The views expressed on Skeptically Speaking are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Schell gonna raise a little hell, metaphorically that is. Cause we're skeptically speaking.
Hello and welcome to Skeptically Speaking. I'm your host, Desiree Schell. This week we're talking about computers and programming, and the cutting-edge research that's blurring the lines between code and cognition. A little later, guest host Rachelle Saunders talks to Sergei Maslov, a researcher in computational biology at the Brookhaven National Laboratory, and we'll learn about the similarities between computer code and genetic information. And she'll also speak to software professional Mark Bennett about his passion for programming and coding as a career or as a hobby. But first, I'm joined by Stephen Gold, Vice President of Watson Solutions at IBM Software Group. As a member of the senior leadership team, he's working to help commercialize industry solutions based on IBM's transformative Watson technology. And I'm very excited. Thanks very much for being here, Stephen.
Desiree, it's a pleasure to be with you.
Now, what is Watson, sir? Give us the rundown.
Watson is really a new class of industry-specific analytical solutions. So that's a little bit of a mouthful, but if we think about it, a new class because it's unlike anything we've seen before in computing technology. Industry-specific because it's addressing the needs across a variety of business requirements and use cases. We can talk a little bit more about how we're putting it to work. Right, and it's based on technologies, candidly, that have been around and have been established for a considerable period of time. Now, what's interesting, to me at least, about Watson, it's really helping to usher in a whole new era of computing. What most of us are used to is programmatic computing. And so really with, I think, the commercialization of Fortran 60-some years ago, what we've seen evolve is programmatic systems represented in terms of how payroll is managed, how operations is run. And for the first time ever, we see this new era of computing, a cognitive era where systems actually operate more like individual systems that are capable of navigating natural language. So understanding the way you and I would typically speak. Systems that are capable of ingesting vast amounts of unstructured data, the type of data we'd find in text and tweets and blogs and surveys, and putting meaning to it, being able to find content in context. So unlike search, which brings back matches to keywords, Watson is capable of actually understanding the intent of the question or query and bringing back relevant information and then weighting it with confidence as to its belief that the response matches what the individual was asking or seeking. And then I think the third part, and certainly to me the most exciting, is systems that learn. So unlike the programmatic era, where systems were literally hard-coded, Watson is taught. We provided training cases, and with each training case, we provided the correct answer, and from that, it's able to advance its understanding of that information, what we would call the corpus or the knowledge of data that it's going against. And it gets smarter with outcomes and iterations and activities. And so these are systems that are going to be able to do things that, historically had not been done by computer systems.
So I'm curious, there's definitely been sort of a focus on the fact that it can answer questions posed in natural language. So why is that so important?
Well, if you think about natural language, things that are inherently obvious and intuitive to us as individuals have, long challenged computer systems. So, for example, how can a house burn up as it burns down? Now, we wouldn't think twice of that statement.
Right.
Why is it that noses run but feet smell? Computers would have said, well, it would be the opposite. And so, these little twists in language, these idiosyncrasies, these colloquialisms have long been the bastion of understanding to a computer being able to comprehend, right, that knowledge. So computers historically have gone against structured data, information residing in rows and columns represented in binary form, easily interpretable and quickly digestible and searchable. Watson like you and I would have a conversation is literally taking it in and understanding, but it can do so at massive scale. So, for example, when Watson was first debuted on Jeopardy, it was literally searching and deciphering 200 million pages of data in a little under 3 seconds. Now, in that particular case, it was tuned for 3 seconds because that's how long it took the host to read the question, and you couldn't buzz in with the answer before the question had been completed. Today, as we commercialize Watson, we once again optimize it for that particular instance and how it's being applied. But certainly for an individual, when we think about natural language, we think about information that's addressable through natural language. The 90% of the world's data has been created in the last 2 years. 80% of that data is unstructured, right? That's a vast repository of insights to be mined for greater insights, for greater outcomes, for actionable activities. So, that aspect, natural language in and of itself is a significant feat, right? Being able to iterate with humans. Mm-hmm. But then combining that with understanding, with this comprehension and being able to retrieve not just answers. One of the things that's interesting about Watson, it's not deterministic. Most systems that we have been accustomed to are looking for the answer, right? So as individuals, we would say 2 + 2 is, and very quickly all of us in the audience are thinking 4. Watson would say maybe. Now, some of us would snicker and say, well, then it's not too smart. But for Watson, a probabilistic system, it says, well, 2 + 2 could be 4 in the proper context, but what if it was an automotive engineer talking about a car configuration, 2 front seats and 2 back seats? What if it was a family psychologist talking about a family unit, 2 parents, 2 children? If you were in Vegas, 2 + 2 is a poker strategy. So 2 + 2 has a lot more interpretations depending on the context, and being a probabilistic system, Watson understands that it needs to evaluate all those possible responses, weight them using analytics and advanced algorithms, and then bring back that information for the individual who's using the system to make a decision.
So walk me through how that looked on Jeopardy.
For Jeopardy, this really began in late 2006 as a research project. And about every 10 years, IBM takes on a grand challenge. And I think some of the listeners may remember the last grand challenge was the chess-playing computer, Deep Blue,
right,
which defeated Garry Kasparov. And, the challenge here was to do something that a computer had never done before. And just as we just described moments ago, really have the system compete in a forum, that would put it to the test relative to natural language and understanding, ingesting massive forms of information, and then, quickly understanding and learning from that to compete against the most proficient players in the world. In the case of Jeopardy, we competed against the 2, grand champions, the individual who had won the most money and the individual who had the longest winning streak. And for 4.5 years, researchers advanced the use of computational linguistics, a way to say natural language. It advanced the use of algorithms and analytics. It advanced the use of machine learning. And in fact, Watson is a composite. It's 41 subsystems in total that research, if you will, formulated the recipe on how to bring all of this technology together. And, really Jeopardy represented a proof point, right, to demonstrate in public whether or not a computer was in fact capable of doing this, much the way the Deep Blue system had played chess. And so years from now, we'll look back and say, well, of course computers can do this. But at that moment in time, millions, tens of millions of people bore witness to, a system competing in a way that had never been done. And, it was really at that junction where we began to think about the commercial applications, because up through that point, it wasn't clear whether or not this was even commercially feasible.
Well, and that's what I find so interesting because, may I say, that was a brilliant piece of science outreach. But Watson is far more important than as just a Jeopardy champion. There's some amazing things that you're doing.
No question. In fact, very exciting, what we have been working on, really over the past 18 months on the commercial front. Our first focus was on healthcare. Within healthcare, medical information doubles every 5 years. So, think about an individual going through medical school. By the time they complete their training, information would have doubled. The average physician, 81% of all physicians report spending 5 hours or less per month, reading periodicals and journals and keeping up just because of the demanding schedule. And so we saw an opportunity, right, in an information-rich area where there was a lot at stake, where 1 in 5 diagnoses are wrong. Imagine sitting in the waiting room with 10 people, recognizing that 2 of 10 of you will be, misdiagnosed. Now, while not always life-threatening, certainly opportunity for significant personal improvement, right, eliminating inefficiencies and waste, right, and really fulfilling an opportunity to do something truly meaningful. And so Watson has been at work with in the medical arena with our partners, for example, Memorial Sloan Kettering. MSK is one of the foremost authorities, certainly in the diagnosis and treatment of cancer, and working with Memorial Sloan Kettering and WellPoint, one of the nation's largest insurance companies. We have developed an application that assists oncologists with identifying the various treatments associated with an individual's symptoms. So Watson's able to cull through, literally the patient history and the records and various journals and articles and trials and best practices and guidelines and regulatory requirements to very quickly share with the oncologist the different course of treatments that would be relevant. And what's really interesting is Watson does that with complete transparency. It's a humble genius, willing to share how it derived and got to the answer. And so it's really the individual then that will make the determination, or in this case, the oncologist with the patient will make the determination what course is best suited. But Watson then becomes this ultimate assistant.
So is this actually being used in hospitals, or is this sort of in beta still?
On February 8th, we actually had an opportunity to formally announce that we were launching the commercial efforts, so moving outside of the development with our partner WellPoint and Memorial Sloan Kettering. And we have begun to take this to additional institutions, community cancer centers and others that are working with us to continue to advance, the use of Watson in this capacity. And this is only, one dimension of medicine. We've announced we're a Cleveland clinic working with students preparing for the medical license exam. So Watson's helping them prepare, and as they prepare, Watson's learning. We're also, looking at ways in which we can make the system more efficient. So Watson today within WellPoint is helping physicians and insurance plans to evaluate and process the various treatment and test requests that are sent over. And then there's other areas like research where, Watson is being pointed as well. And this is all just in healthcare, right? And certainly there are so many more potential opportunities and use cases to take this technology out to industry and across practices to really alter the way, we as individuals, operate and come to expect that we'll be treated. To be bold, I can envision a day when, as a patient, right, I will only want to patronize those that have this type of capability, a Watson type capability, and that deep resource and that ability to query a system to find the best possible, course of action for me as an individual. The personalization and democratization of medicine.
Like you're envisioning, sir.
Well, thank you. You can tell we're excited about what we're doing, and deeply impassioned about the possibilities of where this will go.
Stephen, thanks very much for coming.
That's right. It's been my pleasure. Thank you for having me.
We'll have a link to more information about Watson on our website at skepticallyspeaking.com. And next up, Rachelle Saunders talks with Sergei Maslov on the similarities between genetics and computer code. Enjoy.
Skeptically Speaking is rebroadcast on a number of fine radio stations. To find out where Skeptically Speaking airs near you, to listen to past episodes, or download the weekly podcast, check out our website at skepticallyspeaking.com. While you're there, follow the links to connect with us on our Facebook page, our Twitter feed, or to subscribe to the show in iTunes. And now, back to the show.
This is Skeptically Speaking. I'm Rachelle Saunders, guest hosting today for Desiree Schell. We've done more than a few shows on the theory of evolution, its history, the inner workings of the theory itself, and even taken a few speculative looks at where evolution might take us in the future. Evolution is a given for all living things. But what about computers? Both computers and software are getting more and more complex, and even though computers aren't alive in the same way we are, sometimes the ways they work and interact can look an awful lot like evolution. I'm joined by Sergei Maslov, a tenured staff member and computational biology group leader at the Biosciences Department of Brookhaven National Laboratory, an adjunct professor and executive member of the Lafleur Center for Physical and Quantitative Biology at Stony Brook University, and a co-leader of the K-BASE project. His research concentrates on predictive modeling of complex biomolecular processes and their underlying networks. Sergei, great to have you on the show.
Great to hear you, Rachelle.
So tell me a little bit about your research that finds similarities between computer code and genetic code.
I am really interested in properties of complex systems and their underlying networks. And so because of this, I tend to compare different complex systems to each other. And one of the things which piqued my interest is that I was working with Linux operating system. And Linux operating system is a large-scale open-source software project, which can. And if you look into a description of a Linux project, you will see that there are plenty of individual software packages written by software engineers all over the world, and they are connected to each other through a complex and very interdependent network of mutual dependencies. So they do not work alone. If you try to install one of those software packages on your computer, it will ask you to install other packages it depends on. And when I realized this, it actually was remarkably similar to how genes encoded in individual genomes work. They also do not work alone. They depend on each other for their function, and they are connected by a complex dependency networks. Some of those networks we don't really know right now, but we are learning them by doing large-scale experimentation. And so what I was trying to do is I was trying to compare Linux computers to genes and bacterial genomes and find some similarities. And to my surprise, I found not only that they are similar, but in some aspects they are nearly identical. If you are having a Linux computer, you can individually install those software packages. And your choice of software packages will reflect your preferences in computer software, or maybe your interests. So if you are something like me, the first thing you will install on your Linux computer would be an internet browser like Firefox. And in order to install a Firefox browser, you will have to install something on a scale of 100 of lower level packages on which Firefox depends on for its function. And this is very similar to how you would proceed if you are trying to add a particular gene to a bacterial genome. Just adding an individual gene would almost never allow you to perform a certain function. You need to install a whole series of genes, and only after this you will be able to perform this function. So we decided to compare those two systems, and the first data we found where we can directly compare them to each other is the frequency of installation of packages on Linux computers, and that would be compared to frequency with which a particular gene or gene family is present or absent from bacterial genomes. Both of them are described in terms of certain U-shaped distributions. There are some genes or some software packages which are present in virtually all of the systems, almost 100% of the systems. And this is what we call core packages or core genes. And then beyond those core packages, there are progressively less and less frequent genes or packages which are performing progressively more and more esoteric or specific functions. And there is, in fact, a power law distribution in the frequency of installation of packages and genes beyond those core genes. So when we really compared those distribution of frequencies, we found that they agree with each other to a remarkable degree. That was the first surprise, and that prompted us to do some modeling. My background is actually statistical physics, and as a statistical physicist, I'm trained to try to simplify systems, to try to come up with what I sometimes call spherical cow models, the models which capture the essence of the phenomenon in question, but forget about the details which are less relevant. And it turns out that both software systems and genomes can be described in terms of the same simplified model, relating the frequency of their installation to dependencies, to the pattern of dependencies.
Now, this research specifically applies to just the Linux system so far and not, say, the Windows operating system. What makes them different?
The main difference is that Linux is an open source system, and being an open source, it allows package developers to reuse the packages developed by other people. And in fact, this whole underlying dependency network connecting packages to each other is more of a property of a Linux system than of a Windows system. So a good comparison here would be to think of when you are installing software in your Windows computer, it's usually a proprietary software, and the proprietary software relies on its own developers of, individual software packages. So you can have a lot of redundancies between the packages. You may have, let's say, an internet browser and PDF file reader or something like this. Each of them will rely on their own packages, and they will rarely share those packages with each other. And there is actually a good analogy here that when we are comparing Linux operating system to biological systems, we choose bacterial genomes, and that was done for a reason, because in fact bacterial genomes can be viewed also as an open source genomes in the biological kingdom. The bacterial genomes routinely share genes with each other by the virtue of a process known as horizontal gene transfer. So if one bacterial genome acquired a certain function which is useful to other organisms in the same environment, then it wouldn't take long for this function to propagate throughout the bacterial community. A good analogy here would be a BitTorrent file sharing system where bacterial genomes almost participate in the BitTorrent and sharing genes with each other.
So is this particular to bacterial genomes only, or could this apply to other genomes, like, for instance, the human genome or an animal genome?
This is really widespread in bacterial genomes only. And when I say bacterial genomes, I should properly say bacterial and archaeal genomes, which are two flavors, if you want, of the operating system in the microscopic kingdom. Multicellular organisms like you and me and plants and fungi, multicellular fungi, they participate in this horizontal gene transfer, which is an analog of file sharing, to a much smaller degree. So most of our genes come from our parents and not from the other organisms in our environment.
So this actually kind of boils down to the fundamental way that these bacterial genomes or these bacteria reproduce.
Yes, absolutely. And in fact, the extent to which this horizontal gene transfer shapes up the gene contents of bacterial genomes was not appreciated until we started sequencing complete bacterial genomes sometime in the mid-90s. And then it really hit us how much this horizontal gene transfer is dominant mechanism of evolution of bacterial genomes.
Okay, but a Linux computer system can't reproduce, can it?
No, it cannot. And that is, of course, a very big difference. And some of the features of bacterial genomes definitely do not have counterparts in Linux. In particular, I wouldn't say that the natural selection plays such a big role in evolution of Linux systems. In bacterial genomes, almost 4 billion years of evolution created a complex interdependency network between the genes. Whereas in the case of Linux computer system, it was a collective work of many software engineers all over the world created this network. Once the network is created and shaped by natural selection in the biological domain or some version of technological selection in the computer domain, we are free to reuse parts of this network on our own computers. You or me are free to pick up certain packages and ignore other packages when we select what will be installed on our computers. The same is true for bacteria. Bacteria select their gene repertoire based on what they need in order to survive in a particular environment.
So this survival of the fittest idea with the Linux computer systems, is it something that was consciously built in, or has it sort of emerged over time?
To the extent it applies to Linux computers, it emerged over time. In this sense, this analogy between the biological and technological evolution is incomplete. Rather, I would say the closer analogy would be our choice of what to install on our computers from this vast network of interconnected packages.
You're listening to Skeptically Speaking with guest host Rachelle Saunders, and I'm talking to Sergei Maslov about his research that finds similarities between Linux computer software and the genome. So what are you talking about when you say dependency network?
It is really very easy to formalize this concept of inter-package dependencies for Linux, because when software engineers were writing a particular software package for Linux, they were reusing previously existing packages, and they were formalizing it by saying that in order for this package to operate, you have to install such and such and such packages on your computer. And this can be captured as a network simply because this is a pairwise relationship between the components.
So product D won't work unless you've also got product A, B, and C involved or installed already.
Exactly. And in the previous flavors of Linux, when you were trying to install some sufficiently high-level package, it was explicitly asking you, now it's your turn to install other packages A, B, and C. And this was sort of a chain reaction, because some of those packages A, B, and C themselves depended on other packages D, E, and F. So in order to install something high level as Firefox, you had to install literally dozens of lower level packages.
So you argue in your paper that the observations in your study might be a universal property of any multi-component or multi-layered complex system. Do you have any other examples of these kinds of systems that it might apply?
Yes. In fact, unfortunately, we don't really have the large-scale data for those systems. But one good example of such system are economies of the world, or for individual countries. One way to think about those economies is that there are different sort of technological components of the economy which do not work in isolation. So in order to build a factory which for instance, manufactures computer chips, you need to have a certain low-level infrastructure in the country or in the region where you're building this factory, the roads, electricity, and so on. And so this all can be captured in a dependency network between the components of an economy. Another good example of those interdependencies is knowledge. And again, the problem here is that it's sometimes rather difficult to capture those dependencies. We were really lucky with Linux because those dependencies are captured by software engineers and they are easily available. I can just go to the website for Linux project and download this dependency network. For other things which are more abstract, I have to sort of reconstruct this dependency network to the best of my knowledge. But a good example would be a scientific or technological knowledge. Think of patents. A lot of patents depend on other patents which were created before, and this is an example of dependency network. Something like the internet wouldn't be able to exist if there were not a number of previous inventions which built the groundwork for the internet.
So the only thing right now that's sort of stopping us from, or stopping you, I guess, from testing this or checking is sort of a lack of data in these fields.
Yes and no. For some systems, like for instance, scientific publications, we do have data we capture, to some extent captures this dependency network. For instance, for scientific publications, that would be a network of citations of articles. And this partially captures what we need in order to apply our theory, because when an article A cites an older article B, then in some sense it builds on top of the knowledge reported in the article B. And this is somewhat analogous to this dependency network of software packages, but the analogy is not really complete here because this borrowing of knowledge is somewhat more nebulous than a very rigorous dependency required for software packages to operate.
There's not the sort of failure point of this won't work unless you have this.
Exactly. And also, unlike software packages, you cannot run those experiments. For software packages, I can literally test how they will perform if I will install a certain subset of packages on a brand new computer which I just bought and which doesn't have anything installed. For scientific knowledge, I cannot sort of run those experiments. I cannot really imagine what will happen if I only have access to a subset of articles and not to others.
There's always something there that you can't test.
That's correct.
So this isn't the first time computer code has been compared to genetics on some level. There are actually some similarities in how computer code works at a base level in computer instances with zeros and ones and the chemical alphabet we use to decode DNA, right?
Yes. In fact, my PhD student, Kun-Kyu Yan, who is right now working in the group of Mark Gersten at Yale University, about 2 years ago, they wrote another article comparing a regulatory network in bacterial genomes to code in Linux operating systems. So and in this project, among other things, they were really checking the patterns of low-level evolution, which you are just referring to. In other words, they were comparing the substitutions in the genetic code, which is how the genes evolve from one organism to another, with the frequency of updates of software packages. We did not attempt this in this paper, but this is another very constructive way of comparing biological and technological systems.
So going back a little bit, you actually got your PhD in theoretical physics and then moved towards biology. And you say on your website that you sometimes use tools from statistical physics. How are these tools from your background in physics helpful in your exploration of computational biology?
Well, the biology, especially modern computational biology, is really a big data science. So we are working with large data sets, and the statistical physics is an excellent training for this because statistical physics is a branch of physics which only working when your data set is large enough. So when you can apply the statistical analysis as opposed to individual analysis of individual electrons or materials. So this is really a perfect training, and that explains why so many statistical physicists really became big data scientists. Not necessarily in biology. You see statistical physicists working on analysis of social networks. You see statistical physicists working on financial price fluctuations and so on and so forth. Throughout my career, in fact, I explored a number of interdisciplinary applications of statistical physics. And I would say that I settled on biology as my main thrust area only about 10 years ago.
Now, you're involved with the K-Base project. Can you tell us a little bit about it?
I'm very excited to be one of the 4 leaders of the K-Base project. This is a very large open source project, and the purpose of this project is to build a software infrastructure to analyze large scale biological data. This is a new project. We first received our funding about a year and a half ago. It is funded by the US Department of Energy, the Division of Biological and Environmental Research. The people at DOE, at Department of Energy, they are interested in how bacterial systems work. And one of the reasons why they are interested in bacteria, because they want to use bacteria to generate bioenergy, to convert sugars into biofuels. People at DOE are also interested in the environment, and in particular how the climate changes impact the environment. And they are interested in plant systems, again, mostly for bioenergy or environmental objectives. And that is why this K-Base project focuses on bacteria, which is my organism of choice, and the plants, which is something which I am learning right now. And I'm very excited to work on both somewhat simpler objects like bacteria and somewhat more complex eukaryotic objects like plants.
Sergei, thank you so much for being here today.
It is my pleasure.
If you want to learn more about Sergei Maslov, his research, or the K-Base project, you can visit skepticallyspeaking.com, where links to his website and the K-Base website will be available in our show notes.
On the next episode of Skeptically Speaking, we're discussing the function, evolution, and complicated social norms attached to the human female breast. Guest host Rachelle Saunders talks to freelance health and science journalist Florence Williams about her New York Times notable book, Breasts, A Natural and Unnatural History. And researcher and blogger Cy Curious returns to discuss the work of a French researcher who claims that wearing a bra can harm, rather than help, attempts to ward off the effects of gravity. That's next week on Skeptically Speaking, on your local radio station, or online at skepticallyspeaking.com.
This is Skeptically Speaking. I'm Rachelle Saunders, guest hosting today for Desiree Schell. Today, I'm chatting with Mark Bennett, a developer from Edmonton, Alberta, who's worked in the software industry for over 14 years, first as a Java and Python developer, before seeing the light and making the switch to Ruby and JavaScript back in 2008. He organizes an Edmonton-based Ruby meetup, participates in hackups and hackathons, and mentors beginner and novice programmers through Startup Edmonton. Hi, Mark, and welcome to the show.
Thanks very much. It's great to be here.
Just so all our listeners know, I'm coming at this from a mixed perspective. While by night I help create this radio show, by day I work in an IT company and actually know a little code myself, but not nearly enough to claim the title programmer, which probably gives me a 1 foot in and 1 foot out perspective. So, Mark, what first brought you to computer code? How, or perhaps why, did you start in the first place?
I think programming has been something that's been a part of my life since I was a little kid. I remember my dad got a Commodore 64 when I was about 4 or 5 years old, and sitting down with him and typing up programs that were in the back of programming magazines. So it's really been something that I've done for a long time, and I think it's been something that I've shared as a kid with my family, and now it's something I enjoy doing. But it's also something where I feel like there's a bigger community there, and I really enjoy that community aspect and kind of crafting culture of programming.
And you've stuck with it for almost 15 years. What keeps you excited about programming?
There's a couple things that appeal to me about it. Right off the bat, I really just enjoy making things, and especially making things that people use. I love to build an app or build a site or something like that, and then later on see people using it and enjoying it, and having the kind of experience that I imagined when it was first made. So for me, I think that's a big part of it, is that interaction with the people using it. But another part of it is the interaction you have with the other people developing it. Coding, I really look at it as something like a craft. And, you can always be improving how you do it. And the way that you think about how you approach it, the way you communicate and discuss it with other people, pretty much every aspect of it, there's always going to be a way to improve. So I think that's a challenge, and I think it's also where that appeal comes from and how it can really keep me interested over the long run.
Broadly speaking, there seems to be sort of two different types of backgrounds that programmers have. Either they come from a university computing science program, or they tend to be self-taught and have never really had any sort of formal training. Do you find a programmer thinks or works differently due to the kind of background they have? Is one avenue sort of better than the other?
That's a great observation. I really think you're right in that some programmers come to it having had an app or something they want to build and really focusing on the end result, and then kind of work backwards to develop processes and systems and learn techniques that really work for them. On the flip side, you have programmers who've come from maybe a more formal background. They might have a background in math or engineering and things like that, and they're kind of approaching it in terms of having that formal process and really being interested in following that, and using those maths and sciences. So I think they can be very complementary, and you want to focus both on how you're doing things, but also making sure that you're actually doing things. So I think having a mix of those kind of personalities on a team is a great way to work. And even as a developer, I find, I kind of have a half an hour rule. I like to let myself explore a problem for about half an hour and then really commit to doing something or backing off if what I'm doing isn't working. And I think as I've matured as a developer, I've really seen different ways to nurture those different aspects in myself. And I think you see that in a lot of developers. You become more self-aware and aware of how you work and your natural tendencies, and learn how to both harness the parts of your productivity that work well and improve and work around the parts that don't.
Part of the reason I find programming so fascinating is it combines so-called right brain and left brain thinking. It's really logic-based, and yet it takes a lot of creativity.
The more I program, the more I realize that a lot of the technical aspects of it are really just tools. And a lot of what programming becomes is about that creative work and understanding how to use those technical tools that do require that technical understanding, but use them in a creative way, and approach problems in ways maybe that people haven't seen before. So I think perhaps even more than is really acknowledged by the technical community. I think programming is a technical craft. It's a technically creative field.
One of the things I find really interesting about how computers work is the sort of layers of code that go into making everything function. It's not just one language working away, it's actually several different layers of languages, right?
Oh, absolutely. I mean, if you look at something, one of the big challenges in computing science is taking an application or an app or a product and breaking it down, but finding the right abstractions for the problem. Because having an abstraction at the right layer can really make you productive and help you build an app quickly and develop something that you enjoy and have a pleasant experience both building and using. Whereas on the flip side, having the wrong abstraction or working at the wrong layer can really slow you down and make things a lot more complicated. So for example, if I'm building an application for my phone, when I'm looking at that, I'm going to focus on a very high level and worry about things like, what does the app look like? What happens when you click a button? And by doing that, it allows me to really focus on the problem that I'm interested in. Having said that, I think there are definitely times when being able to cross those layers and dig down into the system or step back and look at the big picture can be really helpful. But learning how and when to do that is part of the craft of programming.
Okay, what do you mean when you talk about abstraction?
A lot of programming languages, really what they do is provide vocabulary and a way of looking and approaching a problem. So when I'm talking about an abstraction, what I'm really talking about is the concepts and ideas and kind of constructs that are in a language that enable you to do that. So for example, there's some kinds of languages called object-oriented languages. Those are ones like Java, C++, C#, ones that a lot of applications are programmed in every day. And those are all centered around the idea of an object having a set of data, so it knows things about itself, and also a set of behaviors. So for example, if I was a car, I would maybe know that I have 4 passengers, I have an engine, I have a steering wheel, and I also know that I can drive, I can move, I can do things like that. So there's a whole family of object-oriented languages that focus on approaching problems from the perspective of objects. There's also tons of other different kinds of abstractions out there to do very similar things, but approached in a very different way. Another example is something called functional programming languages. These are things where everything is viewed as a series of functions with inputs and outputs. And you can go and take these functions and combine them together to make larger applications. So probably the most popular and most common functional programming language that a lot of people see is JavaScript. And it's interesting because it's kind of like a language that has a bit of an identity complex. It looks like it's an object-oriented language when you first start using it, and it actually presents a lot of the same ideas as many other object-oriented languages. But when you actually get into it, it really is a lot more focused on working with functions. So those are just some examples of the different kind of abstractions that you can work with.
So having dabbled a little bit in programming myself, I know firsthand that one of the biggest challenges to newbie coders isn't always learning the language itself. I'm talking about like the syntax, the semicolons, where the brackets and stuff go, but actually how to think about problems in the same way that computers do. How exactly do computers think differently than we do?
Computers are really good at thinking very literally and in a very linear way. So whereas humans are really good at thinking analytically and creatively and dealing with things that are kind of outside of our experience, computers have to be told explicitly what they're looking at and how to handle it. So one of the biggest challenges is really being able to go and imagine an algorithm or something like that and break it down into those small details that are clear enough for a computer to understand, and learning for different programming languages how you can do that and the different ways of doing that. It can be really intimidating when you first start out, because it takes you a while to learn a new language, because you're not just learning the syntax, you're learning literally dozens and dozens of new words to program in it, but also all of the libraries and all of the code around it. So learning how to put those together and to come up with a solution can take a while. And I think that's one of those things where when you're looking at a language, it's important that it has a clear, readable syntax, but it's also equally important that it has a really good set of libraries and a great community behind it. So those are always things that I look for when I'm trying to figure out the language that I'll be the most productive in.
I found this quote by Donald Knuth in American Mathematical Monthly. He says, "It has often been said that a person does not really understand something until he teaches it to someone else. Actually, a person does not really understand something until after teaching it to a computer." Does that seem right to you?
Definitely. There can be days where you spend the entire day trying to take a mathematical concept or a process that you as a person can do almost subconsciously and break it down into a way that a computer can understand and do correctly. Again, I think it comes back to that idea that computers are really literal, and sometimes they're literal to the point of it being really frustrating, because they will do things even when they make no sense to a person. And so for me, a lot of the time, what I focus on is trying to decide, am I feeling productive right now? And talking to other people, asking them what makes them productive, and trying it out. Because really, I think a good language is one that you feel like you're solving problems that you care about. And most programmers could debate for days the advantages and disadvantages of different languages and which one's the right language to program in. And really, I think what it comes down to is finding one that you're comfortable with and that solves the problems you care about.
You mentioned the word algorithm. When most people think of the term algorithm, I know I envision a complex math formula scrawled on chalkboard somewhere. What is an algorithm, and do I need a PhD in math to understand one?
Definitely not. There definitely are complex algorithms out there, but really an algorithm is just a set of instructions given to a computer. So it can be as simple as a statement that says print hello world. You can definitely get more complicated ones, and there's definitely ones where I probably wouldn't try to program them myself. I would find someone who knows how to do that. But I don't think being intimidated by the word algorithm is anything that people really need to worry about.
You're listening to Skeptically Speaking with Rachelle Saunders. We're talking with Mark Bennett, Edmonton-based software developer and lover of all things code. So where do you start? I mean, if you wanted to, say, code a piece of software for a science radio show, where would you get started? What's the first step?
The first thing I like to do is actually close my laptop and step back from my computer and figure out, if I'm the user, what do I actually care about? Or in this case, I would probably sit down with you and get a cup of coffee maybe and really walk through that. Try to understand how you're going to use it. From there, I like to grab a sheet of paper and really try to do a bit of drawing, maybe design things, and do almost like prototypes with a sheet of paper and a pen. It's really cheap, it's really fast, and it's something that everyone understands. Just taking half an hour to do that can do so much to help make sure that when you actually start programming, you know what you're going to build and you know you're building the right thing. Once I'm actually building the code, I really like to go back to that a lot and focus on producing things as often as possible and getting them to a customer. Because one of the biggest challenges I see too is that customers aren't software developers. And a lot of them, unless they work with programmers every day, have a lot of trouble envisioning an application and really understanding how it will work and interact, and how what they're asking for will have an impact on it. So producing something early and delivering it early gives them a chance to actually play with it and understand what they're looking for and to provide that feedback to you. So I really believe in getting feedback as early and as often as possible.
Okay, how often do you take the wrong path and then have to go back and do everything you've already done again?
Oh, all the time. I think it's part of being a programmer, and it's one of the probably the joys of actually being a programmer is that a lot of the time doing that is something that doesn't have a big cost. And one of the ways that we make sure that that's true is, like I say, releasing things a lot. So, for example, if I'm building a web application and I know it's going to be a larger, multi-month project, what I'll do is I'll actually go and try to get that out in front of the customer every week. So we'll sit down, we'll look at what's happening and make sure that if there's things where we're going off track or we're building something that just isn't working, that the team knows that right away. And as a group, we figure out what's possible and what makes sense and try to get back on course as soon as possible.
We've talked to some mathematicians on the show before, and the concept of elegance has come up. Finding the elegant solution to a problem, for example. And the same concept actually comes up in programming, doesn't it?
Absolutely. I know programmers that spend literally half of their time trying to figure out not is this a solution to a problem, but is this the best solution to a problem? And one of the biggest challenges in doing that is there's so many different definitions of what is the best. Is it the fastest? Is it the shortest? Is it the easiest to read or maintain? Because there's different value to all of those depending on the programmer and the situation. So for me, I used to focus a lot on writing the shortest, most concise, fastest code. And one of the things that I've realized is coming back to code like that a year or two later, it can be completely baffling what it was doing. So now for me, it's important that I write code that's concise and that does what I want it to, but it's almost as important that it's clear what it's doing. And so another developer or myself in the future coming back to it can understand it. I find doing that and making readable code also helps me understand the problem better. If you're struggling to create code that you can explain and understand on an intuitive and simple level, it often means you don't really understand the problem. So by stepping back and really thinking about the problem, I can often come up with a better solution in my code.
One of the biggest steps for me as I learn more about programming has actually been thinking more about the kind of larger general case than the more specific problem I'm trying to solve. Why is this important to think about when programming?
When I think about a problem, I tend to think about two different approaches to it. One, I like to think of the ideal and the expected case. So what are the things that we would expect a user to do? What are the things that I would want to do? And build the program with those in mind. And by doing that, you can make sure that when a user is using an application, they're going to have the best experience possible. At the same time, there's also all sorts of cases where users go and push things to the boundary. There could be things like internet going out or cases where they just put in an input that you didn't expect. So the other set of things I do when I'm building an application is really try to think about all of those unexpected or error cases and make sure that I'm at least considering what happens and testing the code to see how it responds. So there's really two paths there, the expected and the exceptional. And by thinking about both of them, you can make a program that's going to work well and be enjoyable even when something goes wrong.
Okay, one of the things we hear some developers talking about is scaling and the problems around scaling. What does it mean for code to scale?
It's something that comes up a lot, especially with web applications, where we have a website that has servers somewhere out there in the cloud that are providing that site. When you have even a few hundred users, often you can do that and not have to worry at all about the amount of computation and servers that you need to support it. The problem is when you start to get thousands or hundreds of thousands or millions of sites. In fact, I think Facebook now has 1 billion users. So when you start to hit numbers like that, you actually run into these cases where you really have to spend a lot of time thinking about not does your application just work, but how does it work when you have 1,000 or 1 million or 1 billion users using it at the same time? Because you can end up with really bizarre situations where, for example, if I go to buy something and it's the very last one, in that fraction of a second that I was purchasing it, another person can have tried to purchase it too. So you have to have a lot of coordination and a lot of different infrastructure and really interesting challenges there to make sure that that all works and works together, and that when you go from 1 to 1 million, it's all still going to work. So when we're talking about scale, that's usually what we're talking about. It's just massive numbers of people, a lot of things happening at once, and just a lot of data.
How much of this long-term thinking do you actually do when you're sitting down and planning something? I mean, there's got to be some kind of prototype phase where you're really just thinking, I got to get this to work. But there must be a phase or a step at which point you need to start thinking about how this is going to work for 10,000 people rather than just 100.
One of the ways that I've really dealt with that is by focusing on tools that have already thought about the scaling for me. So if I'm using a platform like Ruby, then I tend to use frameworks like Ruby on Rails that have already thought about that first. Twitter was one of the classic examples of a Ruby on Rails application that didn't scale well. Whether that's true or not, I think it's caused the Ruby on Rails community to really think a lot about how Ruby on Rails applications scale and provide the hooks and the tools so when scaling becomes a problem, you have ways to deal with it. There's lots of other similar tools for different platforms. So whether you're a Java or .NET or Python, all of those have these kind of frameworks where they let you be productive when you're first starting out. But as it gets bigger and you care more about scale, they have solutions there. That said, there are definitely things that you can do which will make your life easier when you do get to the point where scaling is an issue. And there's definitely things to avoid if you think scale is going to be an issue later. So as a developer, I think what you have to do is just learn what those are. And usually that means going through the pain of making some mistakes and learning how to handle them. Having said that, most applications that I've seen, as scale becomes more of a problem, they usually also have a lot more income and they can afford to hire a few more developers to get through it.
You are tuned in to Skeptically Speaking with Rachelle Saunders, and we're talking with software developer and computer programmer Mark Bennett. Okay, something else I'm curious about, especially because I work with developers every day. If I were to draw a pie chart of how much time you spend writing code versus how much time you spend debugging code, what would my pie chart actually look like?
For every 1 or 2 lines of code that I write, I probably have rewritten them at least 10 times. Because it really is one of those things where you spend a lot of time looking at a problem, trying to understand the crazy computations that a computer could be doing and what the different parts and different moving pieces are doing, and then just making small tweaks. So a lot of the time I'll have things like a test suite where I'll go and make one small change and then see how the application responds, make sure everything is still coming up as passing, it's coming up green is what they say. And as long as I'm still seeing that, then I'll make another change and kind of iterate through that. So it means it's a slow, steady, kind of well thought out process as you develop. So that can be one of the hardest things for people watching a programmer work. You might see 2 developers sit there for half an hour discussing different algorithms and different approaches and different ways to do something, and then write 4 or 5 lines of code to do them. But I'm of the opinion that taking the time to do that is going to reduce the bugs later. And there's nothing worse than having code that's out there and you have people using and freaking out because it's broken and it's not doing what it's supposed to. And it's making their lives painful. And trust me, it's going to make it a lot worse for you when you have to fix that in production.
Mark, it's been great having you on the show.
Thank you very much.
If you want to learn more about Mark Bennett, you can visit markbennett.ca or go to skepticallyspeaking.com, where a link to his website will be available in our show notes. And since you're there, you can also click the links to our Facebook page, our Google Plus page, and our Twitter feed, where you can keep up with the latest from the Skeptically Speaking team. You can also visit us on iTunes, where you can download our past episodes, subscribe to new shows, and maybe even leave a thoughtful review. Thanks for listening to Skeptically Speaking.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Schell gonna raise a little hell, break the spell of Pavlov's bells. Cause we're skeptically speaking, our mind reading tarot cards and witches, psychics, and their spoon-bending mind tricks. All the humbug, flim-flam, frauds and shams, the charlatan who I don't think you understand. It's the hocus pocus, out of focus locus, eroding the brain, making gains on the hopeless. Let the crystal ball fall smash. trash on the floor. Leave the pieces alone, we don't need them anymore. Just a microscope, telescope, magnifier, reading in between the lines of these lies. Bring it on, the skeptics await your letter, your call, tweet, homing, pigeon, whatever. Desiree Schell gonna raise a little hell, metaphorically that is, cause we're skeptically speaking.
Skeptically Speaking is produced and distributed by Suburban Panic Media. Our guest coordinators are Rachelle Saunders and Ed Haynes. Our social media manager is Chelsea Butler. Helen Quivalon is our publications coordinator. Ryan Bromsgrove is our production manager and assistant editor. Josh Witten is our researcher. The show is edited by K.O. Myers. Our theme song was written and recorded by AOK. And I'm your host, Desiree Schell.